Hello, and welcome to the University of Auckland Developer Student Club's first event. My name is Lin, and I'd like to thank you all for attending. Tonight we have two speakers, Aurélien Géron and Maksim Lin, who'll be talking about machine learning and Flutter, respectively. We'll also have a short Q&A session after each speaker if you have any questions. And as this is our first event, I'll be first talking about our club and introducing who we are and what we kind of do. And so, yeah, onto it. First up, I'd like to introduce our core team. So we have Jiari Lin, who's our club lead. Unfortunately, she can't be here tonight. She's quite upset about that, but she is sick. That's me. We also got Jennifer Lowe, our lovely secretary, Aidan Bergs, our treasurer, Rafaela, our partnership and sponsorship manager, Alex Kennedy, our student advisor, Haruna Jayamani, our tech lead, Peter Godecki, one of the tech team, Matt Moran, also part of the tech team, Josiah Bull, our last tech team member, and finally, Jenny Zhang and Beverly Sun, our two marketing co-leads. So on to sort of what is the DSC. So Developer Student Clubs are university-based community groups for students interested in Google developer technologies. Students from all undergraduate or graduate programs with an interest in growing as a developer are welcome. By joining a DSC, students grow their knowledge in a peer-to-peer learning environment and help to build solutions for local businesses in the community. And the DSC is a global initiative with the University of Auckland chapters having started up this year alongside with our sister chapters across Australia. So we plan to offer technical hands-on workshops to help teach about Google technologies as well as other helpful development skills. We also plan to have professional upskilling seminars with some lovely speakers like we have tonight from Google developers. And also finally, we will plan to offer social networking events for like-minded individuals and industry partners to sort of come together and just have a nice time. So our first event will be upcoming. This is the DSC Retro Game Hackathon, and it's this Sunday actually. And it's been organized with our sister DSC chapters in Melbourne, Sydney, Macquarie, Adelaide, and Monash. And it's planned to be a mini hackathon run across one day. It's very beginner friendly with some provided programs and templates to help you get started. There will also be some industry mentors to help provide support across the day in the Discord, and it'll be an awesome addition to your CV. And it only takes around 12 hours, so we'd love to see you come along. There'll be some cool prizes like Google Watches or Google Home Minis, and a great chance to complete internationally with some of our fellow students in Australia as well. So it'll be great to see you there. So without further ado, I'd like to now introduce our first speaker, Aurélien Géron, who will be talking about machine learning. On to you, Aurélien.
Hi, thanks for the introduction, and hi everyone. I'm very pleased to be giving this talk here. Today I'll give a very, very basic introduction to machine learning and how it relates to artificial intelligence. And also give some examples of applications, and maybe if we have a little bit of time, I'll show you some example code, although it'll just be very, very simple, as this is a first approach for people who've never got their hands dirty with this. Yeah, just for some context, I arrived in New Zealand back in January, just in time, just before the COVID lockdowns, and I'm ecstatic to be here. Just love the country, so right, happy to be joining this community. So all right, so I'll get started and share my screen and with a little presentation. Share my entire screen, share now. Select, go, and you should be seeing my screen now. Can you confirm? All right, perfect. All right, so here we go. So first, before I start with machine learning, I'll put it in context of artificial intelligence and whoops. No, actually, there it is. You all know that there's a ton of amazing applications of AI these days, from self-driving cars to crazy robots and games or programs that can actually learn to play games and solve them, or beating the world champion at the game of Go and so on, or prosthetic limbs, or doing forecasting of the market for and some home appliances and all that. So these are the many applications of machine learning and AI that you can see in the news. But there's actually a ton more where basically anywhere there's some data, people now can use tools from machine learning toolbox to extract information, useful information from that data and act upon it. So I'll show you how it relates to AI. So AI is basically a very kind of umbrella term, which means that you're going to program something that will seem smart from a human's perspective. And this is kind of flexible because what seemed smart from a computer 20 years ago is different from what seems smart today. Like people now are very used to being able to talk to their phone, and ask Siri or whatever to the directions or to purchase something. But I mean, just 10 years ago, this would have seemed like science fiction. So the diameter, the boundary of AI keeps shifting, and there's less and less AI because more and more things seem natural to us. So a more useful definition of AI is some system that observes the environment and then acts in a rational way to maximize the chance of reaching some objective. So if with that kind of formal definition, you can go a little bit further than just seeming smart. And talk about, okay, how is something going to act rationally to drive a car, or how's it going to act rationally to forecast the market, and so on. So you kind of get the feeling that you're going to have to define the objective, and very often that's the very first step of the project, is to say what exactly are we trying to optimize, and then trying to build a system that does this in a very smart way. Okay, so what is AI? Like here, well, there are various domains of AI, and one of them, the oldest one, is probably called symbolic AI. Maybe some of you have heard about that. And here's an example. So you want to program a computer to play tic-tac-toe. And a very simple approach for that is to just, say it's the computer's turn right now. It can just look at all the various things it can play and look at the outcome. And then imagine, if I played this first move, what can the human player play? And then, you get basically a tree of possibilities. And then it can look at the final outcome and decide, roll back up to the top and decide, based on what it knows the outcomes to be, decide what its first move should be. So this is basically, navigating through a tree, and everything, there's no fuzziness, right? It's all very strict with very clear positions at each step. And there's, a lot of things you can do with that, and it does seem smart when you play against it. It, will beat you every time. So it is part of artificial intelligence, but it's kind of rigid, if you see what I mean. Now, just to get the definitions out of the way, when we talk about strong AI or general AI, that's something that's really truly smart. That just doesn't seem smart. It truly is. Basically, it can do any intellectual task that a human can. That's the definition of strong AI or general AI. And so far, it's still a distant dream. We're getting closer every day. But some researchers think we will reach this goal in 20 years or 15 years. Others think it's never going to happen, and many think it's at least a few decades off. And okay, so there are various ways of programming an artificial intelligence. And one question you might ask is how, what makes humans so smart? And one answer, not the only one, but one answer is that they can learn. And at first you don't succeed, and then you make gradual progress, you learn. And so the idea with machine learning is to do the same thing with robots or computer systems, and ensure that they can learn through experience. That is the definition of machine learning. It's a computer system that will learn from experience. Usually what we mean by experience is data, right? So it's going to, you feed it data and it gets better at something. So for a more formal definition, we'll say that learning means getting measurably better at some task. So you have to have some sort of metric to define how good you are. And that's, as I said earlier, one of the first steps. And you need to feed it data. So let's look at an example. Say you want to predict, how happy people are in some countries. Say, for example, Cyprus, from 0 to 10. Some people actually went, say the only thing I tell you is that the GDP per capita is $22,000 over there. This data is very old, by the way. I think it's data from 2000. So it's just an example. Don't take it for literally. Here's actual data that people went around and got from different countries. They asked a lot of people in the street how happy they were on the scale from 0 to 10, and people answered. And you could also measure the GDP per capita in each country. I should add New Zealand there. I actually don't know where it fits. I would assume it's pretty close to Australia, or perhaps happier, who knows. And okay, and so what you do see in this data, looking at a quick glance, is it's kind of noisy, right? It's not very, very clear, but you do see a trend, an upgoing trend. So, unlike what people often say, money does seem to make people a bit happier, although it's not a strict rule, and there's a lot of variation, but you can see a trend. And so humans actually see this straight away because we have a very good system in our brain to analyze visual data. But for a computer, it's not that simple. But suppose that you want to learn from this data and make a prediction for Cyprus, and Cyprus is not in this list. So all you know is that the GDP per capita in Cyprus is $22,000. So I guess it would put it somewhere, near on the left of Korea and on the right of Hungary. And so probably the life satisfaction is going to be somewhere around 5. But looking at the trend, you can do a little bit better and say, okay, it looks like there's a linear trend here. So let's model the whole data. Let's simplify it to a single straight line. And let's try to put this line right in the middle of all these points so that it's as close as can be to all the points. And that's our model. It's our simplified view of the data. The data is noisy, so we'll simplify it and make it linear, because that's what it looks like. And very often you use clues from all sorts of other information you might have gotten other than the raw data that we have here to decide whether you think it's reasonable to model the data in the linear fashion. Once you've done that, once you have your model, well, you can make all sorts of predictions. For Cyprus, you would go ahead and look what point you get at $22,000, and you predict that the happiness is 5.7 in this case. But here I chose a linear model. I could have chosen a more complex model with much more degrees of freedom, right? A straight line has just 2 degrees of freedom. I can change the slope, and I can change the intercept, like the point at which the line crosses the vertical axis. And those are my 2 degrees of freedom. That's all I have. But if I have a more complex model with many, many parameters, like a neural network might have millions of parameters, then I can make it fit the data much more closely. Now, the question is it always better to have more degrees of freedom? Do you trust this model that has a lot of parameters? Do you trust it more than the linear model? I, for one, actually trust the linear model better, because the underlying assumption when I look at this complex model is that everything in happiness is due to money. Like there's no other factor. This is basically what this entails, right? If I think that I can always make a very precise prediction of happiness just based on the GDP per capita, that's the assumption I'm making. And that doesn't seem like a good assumption. So even though my model is more powerful, has more degrees of freedom, and it fits the data more closely, I would actually trust this model better. So it's not always the case that the model that fits the data best is the best model. You need to basically set aside some of the data points, maybe 20% of them, and evaluate various models to see how good they perform on that data that you left aside, okay, which is called validation data. Okay, I hope everything is clear so far. If you want to ask questions while I talk, don't hesitate to do so. I don't know where to read it, but I presume that Hiru might be able to forward the questions as I go. Okay, so far so good. We have a model. Now, this is the question of the simplicity of the model. Usually you want a good trade-off between a very simple model that will generalize well, because if it's super simple, it's very constrained. If it works well on the training data, it's more likely to fit the a random new point that you will get than a very complex model that just happens to fit the training data very well. So you want to find some good intermediate. And as I said, one way to do that is to set some data aside and try various models with various degrees of freedom until you find one that fits the data, the training data well, but also the validation data correctly. So in this case, for example, it seems that there's a plateau where once you have enough money, apparently money isn't the main factor anymore to determine your happiness. So it seems to plateau off around $40,000 per capita, for example. So maybe you want to include that kind of shape for your model and then try to tweak the parameters of that model to fit the data. So what kinds of models are used in practice? Well, all sorts of models. Basically, any model you can invent. The more common one are linear models, especially when data is when you have little data or it's very noisy. Polynomial models, quadratic models, all sorts of models. And SVMs are support vector machines. Those are also fairly popular. Depending on how much data you have and how noisy it is, various models will work. And when you have plenty of data and a significant signal in that data, artificial neural nets are very, very good in that regime. They're not good when you have little data, but when you have millions of data points, artificial neural nets can capture the complexity in that data very well. They're super powerful. As I said, they have millions of parameters, so they might actually overfit the data if you don't have enough data points. So it's important to have big data sets when you're dealing with artificial neural nets. But just to be clear, you don't always need to have big data sets to use machine learning. First, you could use a very simple model, like linear model or so on, and it's still machine learning. And second, you can actually do something called transfer learning and use an artificial neural net that was pre-trained on some data and just fine-tune it on the little data that you have. And this is also very frequent when using artificial neural nets. Okay, so I'll just do a quick dive in artificial neural nets while I have the time. I'm trying to stuff as much information as I can in very little time. So as you know, well, you have neurons, I hope, and they're interconnected. I think each neuron is connected on average to about 10,000 other neurons, and you have something like 100 billion neurons in your brain. So that's quite a lot of connections. And people have tried to model the individual neurons' behavior. And they notice that basically each neuron seems to be doing something fairly simple. It looks like it's doing basically a weighted average of its inputs. So it has, if I look at any one of those artificial neurons, it has arrows coming in. Those are its inputs. And it does a weighted sum of its inputs. So each arrow has a weight. And it does a weighted sum of those inputs. And that's an output after it's been processed through a little so-called activation function. Basically, initially, we used to use a threshold. Like if the weighted sum is above 10 or something, then you output 1, or else you output 0. So it used to be a threshold like this because it was inspired from the brain. The brain seems to have this kind of threshold behavior. So that's how they modeled the artificial neurons. And then they noticed that in the human cortex, there seem to be several layers of neurons, and one layer seems to be connected mostly just to the next layer. And so they thought, okay, let's try to copy that. And this gave rise to the perceptron, which is the architecture, the neural net architecture you're seeing right now. So basically a sequence of layers of neurons. And each neuron just does, as I said, a weighted sum of its inputs. So what does it mean to train a neural net like this? Well, it just means to find the right weights for each parameter, and until the output approaches the desired result. So, by the way, when you see a neural net like this that has 3 layers or more, then it's called a deep neural network. And then you're not talking about machine learning anymore, you're talking about deep learning. So that's how everything fits together. Machine learning is a part of AI, and deep learning is a part of machine learning. Now, machine learning is a field that has like plenty of subfields or fields that feed into it, like from statistics to optimization and big data. Computer science is not in there, it should be, and robotics, AI, and so on. So it's at the intersection of plenty of really interesting things, which makes it fascinating. Now that I've kind of presented the general idea of what machine learning is and different models, how you fit the training data and hope that it can make predictions for new data points as well. Let's see, what it can do. The first thing it can do is what I've just done earlier, was to predict a value, right? So you can estimate, for example, the price of a house given a number of characteristics like its surface area and so on. Or you can do time series forecasting to predict the stock market, although that's pretty tricky. and estimate things like the risk for an illness if you're working in insurance and that kind of thing. That's regression, so it's predicting values. The other application is classification, and that's one of the things I worked on when I worked at YouTube. I was leading the YouTube's classification team, so basically classifying automatically all the videos. Like there are about 2 billion videos at the time, probably 10 times that today. And one of the things we tried to do is find what the topic of the video is. So is it a video about tennis or basketball or golf or whatever? And so there was a team in Mountain View that was specialized in that. That was not our team, but we using the output of their efforts. And what they did is to look at the different frames in the video and take all the individual pixels of an image and feed them as the inputs to a neural net. And then, so it wasn't the architecture that I showed you. It's a convolutional neural net. It's a different kind of architecture, but it's the same kind of principle, where you feed the data in, it makes a prediction at the right-hand side. Basically, each neuron's output on the right-hand side in the output layer is interpreted as a probability. So maybe it'll say, I think it's 90% chance that it's basketball and maybe 5% chance that it's golf and so on. And if it makes a big mistake, then you fix the weights. And there are basically use optimizers for that using something called gradient descent, but I won't get into this level of detail today. But it's basically optimization. You tweak the parameters of the neural net until it fits, to make it fit a little bit better the data, and you keep repeating this until it performs well. And just to show you an example of how it can perform, I hope you can see my screen, or else I'll share the link to the video if you want. So here you'll see on the top, on the top left-hand side, you should see the neural net based only on the frames in the video. Yep. All right, okay. So here you can see like some sports, and on the left-hand side, top left, it's saying, okay, I think it's basketball, and then, oops, no, I think it's wheelchair basketball with about 80% or 70% precision or confidence. The score is the confidence score from 0 to 1. They actually punch themselves out in this case. I love mixed martial arts. And when it gets it wrong, it's actually still in the right ballpark, which I find interesting. And so when the person, like here in the golf, it sees the ball, it says golf, and then it says model aircraft, and when you're back to the ground, it says golf again. So you can tell that it's making reasonable guesses based on the images. And this is just one neural net trained on plenty of images. All right, so just an example. I guess you've already seen plenty of examples of. Well, I'm not sure you've seen videos like that. It's typical YouTube. The guy punches himself out. So it's boxing. All right, so that's it for classification. And both regression and classification that we've just looked at are examples of something called supervised learning. This means that when I give it an example, for example, one image of boxing, I also tell the algorithm that it is boxing, that it should classify it as boxing. And this allows the algorithm to know, how good or bad its prediction is, and therefore to know, how much error it made, and therefore to correct the parameters in the model to make it a little bit better. That's supervised learning. It's when you have not only the inputs, but also the desired outputs, and that's what you feed to the algorithm. And this works really well, and it can learn, to separate these classes using the neural net. But another kind of machine learning that you don't see as often, but which is also pretty useful, is unsupervised learning, where you don't have the so-called labels. You don't tell the algorithm what the desired output is. You just give it plenty of data and just tell it, go ahead with that data and do what you can do. And so one thing it can do is if you feed this data to a clustering algorithm, it'll try to identify groups of instances or examples, if you will, that are similar. And this can be very useful, for example, for client segmentation. If you make T-shirts or something, you might not know exactly what types of clients you have. Maybe you need 3 sizes, or maybe you need 2 different sizes. And using clustering algorithms, that's the kind of thing that you can figure out. And there are some parameters that are different from the ones I talked about, which are called hyperparameters. which determine, those are not tweaked during training. They're prior to training. You say, I expect there to be, say, two groups, or I expect there to be 3 groups. And depending on that hyperparameter, which I call K in this case, you'll get different output. And so, what the hyperparameter should be set to really depends on your final objective, like what exactly is the business objective that you have. All right, so that's supervised learning. That's unsupervised learning. Another example of unsupervised learning algorithm is anomaly detection. Say you feed the algorithm a lot of data, and then you give it new data, and you ask it, does it look like something you've seen before or not? That's anomaly detection. And then there's other things which are like hybrids, semi-supervised learning algorithms. For example, in Google Photos, you upload a bunch of photos without telling it who these people are. But then if you just label a few of them, it will automatically label the others, right? So that's semi-supervised learning. You have reinforcement learning, where the objective of the algorithm is to learn a strategy. So it's going to run around in some environment and make mistakes and take actions in this environment, and get rewards and penalties. And from that sparse rewards, it's going to learn a good behavior to maximize the amount of rewards it gets over time. All right, and lastly, you have recommender systems like you use every day in Twitter, Netflix, Facebook, and you name it. Anytime you have a feed, it learns based on people's behavior, including your own, what to recommend in order to maximize something. For example, the time you spend on YouTube, or how much you click on ads or things like that. And lastly, there's generative, I don't know if you pronounce it this way, generative learning, which aims at generating data, like faces of people that you've never seen before, that kind of thing. All right, I think that probably will give you a headache if I go on for too much. So I believe it's been almost 30 minutes, and I'll probably just take questions, unless maybe you want to see some example code. Actually, yeah, do I have 5 minutes to show some example code?
Yeah, sure, go ahead.
All right, let me zoom in, because you probably can't see this very well. So I'm using a tool, I don't know if you know it, but it's really excellent, called Colab. You go to colab.research.google.com, and it gives you, basically it's hosted Jupyter notebooks. And Jupyter notebooks are these environments where you can actually execute code. I'm pretty sure you all know what this is, but just in case some of you don't, you write code, and you just execute it directly online without having to install anything. So here I've just created a very quick notebook for you. So I assume that a lot of you, if not everyone, is familiar with Python. So here I'm importing the Keras API from the TensorFlow library. And then I'm loading a data set called MNIST. Actually, yeah, let's try MNIST. And sorry. And once I load this data, notice that it's already split in 2 parts: the training data and the validation data that I mentioned earlier. So the training data is what is going to be used to fit my model to the training data. And then once my model is fit to that training data, I'll verify that it works correctly on the validation data. So the validation data is not something that the algorithm is going to see during training. It's just used to verify that the model has learned correctly and that it's not just overfit the training set. Okay, so once I've loaded this data, I'll import a library called matplotlib, which allows me to plot stuff. And I'll call imshow using this PLT library or matplotlib library to display the first image in the training set, right? Xtrain of 0. And I'll use a color map of binary just to show it in black and white. And there you go. So the first image in that training set is a digit that represents the number 5, apparently. The second image is a 0, and so on. Now, what is the second thing here? We have Xtrain, so these are the images, the training images, and Ytrain are the labels. They're the targets. This is what the algorithm should try to predict. So for the first image, it should try to predict the number 5, and for the second image, it should predict 0. So those are just the labels. Now that we have our data, so we have the training data and we have the validation data, let's go ahead and build a model. So for this, I'm using Keras, which is an API, which is available in various deep learning frameworks, not just TensorFlow, but some others like MXNet. And so here I'm using TensorFlow as the underlying deep learning library, which will do the heavy duty, but I'm using Keras as the API because it's a very simple to use API. So from TensorFlow import Keras, and then I'll build my model. So I'm building a sequential model, which means it's just a sequence of layers, one after the other, just like I showed in the diagram. The first thing I do is I flatten each image so that it's just a very long list of pixel values. And that's because the layers that I want to use afterwards are just layers that can deal with one-dimensional, with vectors, not with images, 2D images. So here we go. Oops, it keeps doing this. So once it's flattened, I can pass on the data to the next layer, which has 100 neurons. And it uses the ReLU activation function. That's a technical detail. It's basically how it processes the output of the weighted sum that I mentioned earlier, how each neuron does that. And you need a non-linearity. You need some activation function in there, or else the neural net doesn't work. Because if you pile up a lot of linear layers, they all mathematically are equivalent to one single big linear layer. So it wouldn't make sense. So you need something to kind of skew the output a little bit. And lastly, I have my output layer with 10 neurons. So there's one neuron for each class, right? There are 10 digits, so we need 10 output neurons, one for each class. And I'm using a softmax activation function. This is to ensure that the sum of all the outputs is equal to 1, because I want this to be like a probability distribution. I want to have a probability for each class. All right, I know I'm going very fast, but the point is not for you to learn all this by heart, but just to give you a feel of what it looks like. All right, and next I compile my model, meaning I have to tell it what, a loss function, to give it a loss function. The loss function is basically what will allow the algorithm to know when the model made a good prediction or a bad prediction. And this loss function needs to be differentiable, and you need to be able to compute the gradients of the loss, because that's how the optimizer algorithm works. It will look at the derivative basically and say, oh, okay, if I tweak the parameters slightly in this direction, this should reduce the loss. And so this is the function I use for classification. It's the typical function that's used. And I use an atom optimizer. It's basically a better, optimized version of gradient descent, where you just go and try to tweak the parameters in the direction that will make the loss smaller and smaller. All right, and once you do this, well, you can just call model.fit, give it the training data, the targets, say how many times it should look at this data and go through it, and give it the validation data so that we can just, it's not going to use this in the training algorithm, it's just to display how good we're doing on the validation set as we go. So let's go ahead and launch training. So here it goes. It's going through all these steps. At each step, it's actually processing 32 images. So that's why it has just these 1,875 steps. You have to multiply this by 32 to know the size of the data set. It goes through all of this, and you can see that the loss, this is the error that the model makes on the training data, goes down from 2.4, whatever this means, to 0.41, to 0.29. It's going down, so which is good. It means that we're making less and less error on the training data. But now let's look at the validation loss. This is the error that the model is making on data that it has never seen in training. And here you can see that it is improving as well, but not always, right? Here it's going back up to 0.38. It's kind of bouncing up and down. So overall, it seems to be making progress, but it's not as steady. And that makes sense because the algorithm is learning on the training data. It has never seen the validation data. So maybe the validation data has examples that aren't exactly like the ones it's seeing in the training set. And if you continue training for a very long time, the training loss is going to go down and down and down forever, whereas the validation loss might actually end up going back up. This happens if your model is said to be overfitting the training set. Like it's starting to learn not the general rule, but like the noise in the training data. Okay, so training is done. It was fairly fast. Let's plot, how these are called learning curves, how the loss evolved during training. So this is probably the training loss, and this is the, this must be the training loss, and this is the validation loss, which went back up again a little bit and then down. And you can see that at the end, we're getting a better performance than we had at the beginning. So let's make a prediction now with this R model, now that it's trained, called model.predict. Give it, for example, one image from the validation set, say the very first image, and I'll use numpy.round. This is just to give, actually, let me remove this. It's complex for nothing. Let's call predict on the first image, and it gives me 10 probabilities. This is the probability that the model predicts for the first class 0. This is the probability that it's a 1, and so on. This is the estimated probability. And it's hard to see if you don't round it up. So this is why I called round, to round up to 2 digits. And as you can tell, it's given almost a 0 probability for every class except this one, which must be 0, 1, 2, 3, 4, 5, 6, 7, class number 7. So let's plot the image, and as you can see below, it got the prediction right. It is indeed a 7. So that's about all I had for today. I know it's a lot to take in, and I was a bit too long, but hopefully it gives you a good idea of what machine learning is, how it fits with AI, and what are the applications, and a little code example just to spice things up. All right, any questions?
Awesome. There have been quite a few questions actually, so I hope you don't mind, I'll just be taking the presentation back and we can start looking through some of those. But thank you so much.
My pleasure.
Great.
I'll stop presenting my screen unless we need to come back to the code example.
But yeah, so just for the presentation. Sorry, there we go. So the first of course question we have is this one, if you can see that on my screen.
Yeah, what kind of courses should I take in summer break to start with ML, and what kind of projects can I take up?
Now, I'm sure you know what courses we have at uni, but resources or online that you have. Sorry about that.
It's a tricky question because it really depends on what you already know, right? If you're learning to program Python, you should start with that. Like there's a whole progression until you reach deep learning, and I guess one thing I would recommend is to not jump too fast to the deep learning part. Well, it's a double-edged sword. Let's say that when you jump to deep learning, the nice thing about it is that you can quickly have very, very appealing results, like images that get classified, things that do look like artificial intelligence. So it's very motivating. So if you need motivation, it might be a good idea to start with a little bit of deep learning just to see that, wow, I'm able to do incredible things. But then if what you really want to, you're motivated and you've got time, then I would actually recommend that you make sure you understand the basics very well. And the basics is, really understanding what a model is, what the validation data is there for, what's cross-validation, like more generally understanding machine learning, because I see people jumping directly to deep learning a little bit too fast, because that's where all the fun applications are. But you make sure you get the basics first. So yeah, now there are excellent classes online. I really like Andrew Ng's classes, and so I would recommend doing some of those, and getting your hands dirty is also important. Now, there's one thing I forgot I had a slide with my book. Shameless plug here, but I'd actually recommend my book because it has a bunch of examples, and it takes you, like, my goal was to get people who know how to program in Python, basically, and who have some understanding of math, like matrices and vectors, nothing too complex, but some basics that I'm sure all of you have. Then take people who know only this and get them all the way from up to machine learning and all sorts of algorithms, and then building state-of-the-art deep learning systems. And you have Jupyter notebooks online on my website, and so you can check those out and run the code. It's actually open source, so you can check them out directly. Yeah.
Thank you very much. Awesome, and definitely recommend people, if they are interested in learning more, to check out this book. The next question we have is from Anonymous. Ooh. Can one without statistics knowledge get into the machine learning industry?
Yeah, I guess I would say it's possible to get into the industry and by just having the technical skills to do what I just did earlier, like train a model and that's it. It depends on what you're going to do. Like if you're going to be the engineer, a machine learning engineer who's actually going to take somebody else's models and put them in production, then there are a bunch of skills that are required to actually just productionize those models. And you don't necessarily need to get into all the statistics of the underlying models. Now, if you're going to be the data scientist who actually, comes up with these models and trains them, I would really recommend understanding at least the basics in statistics to play in this field, or else. Yeah, you might get into. It's possible to get away with not knowing much at first, but I think eventually you'll run into cases where you definitely need to understand it well, especially in cases where you don't have that much data, and then it really gets important to understand to define a good model and understand the stats basically.
Awesome, thank you. A bit more sort of technical question now from Kabalan. Is there any way to guess the optimal weightings and thresholds of neurons in a neural network such that the learning you need is minimal, or is it really something you randomize initially and you need to have a good learning algorithm?
That's a great question. Yeah. So if you start with a completely random neural net at first, it will only know about your particular data. So it's like it's learning from scratch. And so what you can do, and like most people do, and whenever they can, is to actually take a neural net that was already trained on somebody else's data, but on some similar problem. So for example, if you're going to train an image classifier, don't start from scratch. Take somebody else's neural net that was trained on, perhaps millions of images of cats and dogs or what have you. And even if you're not training your model on cats and dogs, there are very often visual features that will be common, like in all pictures of natural objects tend to have curves and circles and lines and things like that. And these are things that have already been learned by that other neural net. And so that's when you want to use transfer learning. So very often you don't start training from scratch like I just did. You start from a pre-trained neural net and you go ahead with that. Now there's also research on trying to find how to initialize a neural net in a better way. Like one of the things that kept neural nets completely stuck for a very long time until the current wave. So what caused one of the winters of AI was that the initialization of the weights wasn't properly scaled. Like the weights were either too big or too small. And what happens is a bit like if you chain multiple microphones, right, and amplifiers, if they're all set too loud, it will saturate at the end. If they're set too low, you won't hear the voice at the end. You need all of them to be exactly tuned correctly so that the output can even do something, right? It doesn't saturate or it's not zero. And for a long time, people weren't using this. Like I think Yann Lequin was using this in '98, but it wasn't necessarily common practice. And so, yeah, I hope that answers your question.
Awesome. I think we'll do maybe one or two more. Here's another question. How much data do we need for a machine learning to be useful? What sort of applications need different amounts of data?
That's a very good question. So any kind of data can be useful. It really depends on the task. So there are cases where you have very, very little data. Like for example, you'll have just one image and you want to generate another image based on that. So you have just one data point. And there are other cases where you have millions of data points. For example, YouTube recommendations, they have like billions of videos and millions or hundreds of millions of people coming back to the site all the time. So they have plenty of data, as much as you can imagine. And in both cases, you can do things that are useful. So I don't think there's a threshold for being able to do something useful with data. It's just that it depends on the context, and you will not necessarily use the same kind of models in both cases. Like typically, if you have little data, you won't necessarily go directly to a deep learning model. If you have little, unless you have a pre-trained model, right? If you have a pre-trained model that's available, it's already been fed millions of images, for example, from somebody else, and you happen to have just a few images, that's okay, because you can use a pre-trained model. But if you don't have a pre-trained model and you have little data, or it's noisy data, then typically, neural nets will not function well, and you'll have to resort to some model that doesn't have too many free parameters, or else it's going to just overfit the data. So to quickly give you a rough sketch of the types of models you might use, depending on the amount of data you have. If you have like less than 100 data points or it's noisy, you'll typically use a linear model. And this is really rough around the edges, but just to give an idea, if you go a little bit above, say 1,000 data points, maybe a support vector machine. If you have like 10,000, 50,000, you might use random forests. And if you have beyond that, then you might start to use neural nets. Again, unless you already have a pre-trained model available, in which case, you can start right away, even if you have very few data points.
Awesome.
Okay.
Well, thank you so much, Aurélien, for the amazing talk. We'll probably try to send through a few more questions and maybe post them on the Facebook in a few days if you can get them answered them. But we'll now be moving on to our second speaker, who is Maksim Lin, and he'll be talking about Flutter and Android. So, welcome in.
Just a question, a second. I just want to thanks everybody, and if you want to contact me, please don't hesitate to do so through Twitter. My handle is just my first name and last name, Aurélien Géron. And I'd be happy to answer questions. And if you have some feedback about the talk, I'm happy to take it. Thanks.
Awesome. Thank you so much. Hi, Maksim.
Hi, thanks very much, Flynn. I'll just start sharing my screen. Cool. Hopefully you can all see that.
Yep.
Excellent. So thanks very much. And thanks for the opportunity for being able to speak here with you guys today. So I'm just going to do a quick introduction to Flutter. So sort of just quickly run through all things Flutter and hopefully give you an idea of what it's all about. So first off, I probably should introduce myself. Maksim Lin. I'm a developer here in Melbourne, Australia. Like I've been doing mobile development for around 10 years, and last couple of years I've been doing Flutter development, and more recently through my work in the local GDG and community here, I've become a Flutter Google developer expert. And I should also say that I did actually grow up in New Zealand, so like I'm a bit of a exile here from Wellies, so it's nice to be able to at least speak with you remotely, if not come and visit you in person to give this talk. So today I just want to talk about the three kind of top questions that come up when people want to know about Flutter. They are: what is Flutter, why Flutter, and how do you do Flutter? So I'm going to only have a short period of time with you today, but I'll try and at least give you kind of high-level answers to these three questions to get you started. And first off, I want to cover off what is Flutter. Well, like my favorite way of talking about it, and actually recently the product manager at Google for Flutter mentioned a similar thing, is that think of it as a game engine, but for app development. Now, for those of you who might be familiar with game development, often that's done with these things called game engines, which are essentially SDKs or frameworks to let you more easily build a game. And really, Flutter is a similar sort of thing, but for app development. It started off specifically for mobile development, but as I'll talk about in a second, it's branched out since then. So really, it's all about giving you a toolkit, an SDK, to build really fantastic apps. Now, in terms of the Flutter itself, as I said, it's an SDK, a software development kit. And this is like the kind of stack that makes up the Flutter SDK. I'm not going to talk about even more than one or two of these little boxes, but this really is just intended to give you an idea of what are the major components of Flutter. And that is, the framework is made up of basically a library, a suite of code that's built in Dart. Underneath that sits the engine that's built with mostly C++ and a bit of C code that really does all the kind of heavy lifting. And then there's the embedded layer, which lets Flutter basically run on any particular platform that it's been ported to. So that's basically the stack that makes up Flutter. Now, I said Flutter lets you build apps. What it actually does is let you build native apps. Now, this is a little bit of a contentious assertion because some people like to just only talk about native apps as the apps that are built with the SDK that's provided by the platform vendor. So, for instance, the Android SDK from Google for Android development, likewise the one from Apple for iOS development. But really, a native app is just one that runs natively on the platform, not so much like which SDK or user interface toolkit that's been used to build it. Even more so now that both Android and iOS have newer versions of user interface toolkits or SDKs, if you like, that you can use to build apps that aren't the ones that actually originally shipped on the platform. So my contention is Flutter does let you build native apps, because what it does is the apps that you create with it can be compiled to native Intel or ARM binary code that runs directly on the CPU of whatever device it's running on. There is no, for instance, if you compare it to another similar sort of SDK like React Native, if you may have heard of that, there is no JavaScript engine or bridge that's running your code and bridging it across to the user interface elements of the platform. Basically, Flutter is a native binary running on the platform where it's deployed. Also, what that means is that Flutter is able to provide really nice things like smooth, GPU accelerated 60 frames per second graphics, smooth animations. It's still able to do deep platform integrations with whichever platform, Android, iOS, and so forth, that it's running on. But what the key thing is that it doesn't use what some people call the OEM user interface elements or toolkit that comes, say, on Android or iOS. Flutter has its own user interface that it basically paints pixel by pixel from scratch, and it calls these things widgets, which we'll talk about in a second. But what they do is they set out to match the platform look and feel, but they are their own thing. They are not using Android or iOS's built-in user interface elements to display the app. Now, I mentioned widgets. Well, widgets are the be-all and end-all in Flutter. Basically, widgets are the key concept in Flutter, and almost everything in Flutter, at least in terms of the user interface, is a widget. Now, this is quite different from, say, some other UI toolkits or SDKs where you might have, for instance, a user interface element like say a button or a text field, but then say if you want some padding around it or you want it in a particular layout, those are like separate properties. Well, in Flutter, everything literally is a widget. So if you want to put padding around, say a button, you have a padding widget. If you want to center your button on the screen, you have a center widget that you put the button inside of. So pretty much everything is organized around widgets in Flutter. Now, these widgets are what's called stateless by default, which means like literally they don't have state. Once you've created them, that's it. They're immutable. They stay like that forever. Now, of course, and what that means is that if necessary, every frame, and when I say frame, I mean like frame on the screen. So like when we talk about 60 frames a second, that's like the your app being drawn to the screen in every frame. These widgets can be recreated as necessary per frame. Of course, there are lots of optimizations to make sure that that happens efficiently, but really they can be if necessary. And that's because, like I said, they're immutable. That means they do not, once created, they don't change. Now, of course, your user interface of an app does change. It changes, it reacts to things all the time. So you do have to have state somewhere. And what Flutter does is it introduces another concept called stateful widgets, which are actually stateless widgets that delegate keeping state to another class, to another object. And so what they do is they essentially offload that responsibility of keeping track of state to something else. And stateful widgets are one way of keeping track of state in Flutter. They're kind of like the most basic, if you like, or the built-in way, but there are lots of other ways. And I'll talk about this in a little while. State management, this keeping track of state, is a very important thing in Flutter, and there are lots of approaches to it. And finally, what happens because everything is a widget, so even if you, like I said, if you want to put padding around a widget, what you do is you put that widget inside a padding widget. And then if you want to have that centered, you put that into a center widget. What that implies is that you end up with very deep hierarchies, deep what they call trees of these widgets that create the layout of your user interface. So that's another characteristic of Flutter, is these very deep layouts. For people who may have worked with web development, it's very similar. Often if you do view source on a web page, you will see very, very deeply nested, very deep hierarchies of HTML tags. And Flutter works in a very similar way. It has these very deep trees of widgets. So moving on to why. Why do you care about Flutter? Why would you want to use Flutter? Well, for someone who wants to build apps, Flutter is an excellent tool for high velocity development. It lets you get things done quickly. And it does so with a number of really useful features. One, possibly the killer feature, is stateful hot reload. Now that's a mouthful. What that actually means is that in a lot of scenarios, not all, but a lot, what Flutter lets you do is, as this little animation is showing, is you can actually have a running app. You can change code while that app is running, and Flutter will apply those changes to the running app without losing the state that the app is in. So for instance, in this little animation, what they're showing is, this is showing the starter app, the counter app that basically you get anytime you create a new Flutter project from scratch. What it's showing you is that the state, how many times the user has clicked the button, that's like an in-memory variable somewhere, is actually being maintained. It's not being lost as the code is actually changed. So for instance, I think what this animation shows is the text is being changed. So what that allows you to do is to very rapidly iterate and make lots of quick, small changes to your app and actually see it happening live, but not just that, but also without changing necessarily or restarting the state of your app, which means you can be, say, working on a screen that's actually 2 or 3 levels down in your app. So you've navigated through your app to get to a particular screen, and then you want to make some tweaks to that screen. You can do that. And as you make those changes, you won't lose your state. You won't get kicked out to the beginning. You'll stay in that in that screen of your app that you've navigated through to. Now, alongside that, the stateful hot reload happens very quickly, like under a second. But not in all cases can that happen. Like there are some changes that might be too big, or there are some changes which change the app in such a way where it cannot maintain the state. Or for instance, you're dealing with what I mentioned before, stateful widgets, which are maintaining state in a way where as you make changes, they may not be able to maintain that state. So in that particular case, Flutter also provides you what they call hot restart, which is a restart of the app, but it happens very quickly, like in just 2 or 3 seconds normally, or sometimes even faster, which means that even though you're losing the state of the app, you can still iterate very quickly. And this is, for instance, very similar to a lot of web development where you just reload the web page to see your changes. This is a similar sort of thing. You don't keep the state, but the reload is very quick. In comparison, in, for instance, native Android development, which is what I'm most familiar with, you can often spend quite a bit of time waiting for your code to be recompiled. Then the recompiled code gets packaged up, that package gets pushed onto the device, and then the app gets restarted, and then you finally see the changes you made to the code. So this in itself these two features are a huge win in terms of your productivity as a developer building an app. Now, there's also other tooling involved. There's a fantastic user interface inspector, and it has a great feature which lets you basically click on a particular part of your user interface and actually jump to the code, to your dark code in your app that actually created that part of the user interface, whether it's a button or text form field or something like that, whatever it is. And that's really helpful, especially if you're working on maybe code that you haven't touched for a while, or you're new to a project and you're not familiar with the layout of the code or how the app works. This really lets you become productive very quickly in getting up to speed with what user interface elements come from which parts of the code. Also, Flutter is actually part of this now growing family of frameworks which have what's called reactive unidirectional flow, which I'll get to in a little bit when I talk about how to do Flutter. But basically, it's a particular way of doing user interface software development. And basically, it really got popularized by the React web framework. And now it's spread out to, for instance, Flutter. On the Android native side, Jetpack Compose uses a similar approach, and on iOS, Swift UI is also another new framework from Apple. All of these are very similar because they've all picked up this reactive, declarative, unidirectional flow paradigm for building user interface code. And I've talked about that the widgets are stateless and immutable. What that means is that in a lot of cases, it greatly simplifies you dealing with the code and being able to reason about it. Now, of course, like so far, I haven't really mentioned too much the fact that Flutter is cross-platform, or as I prefer to say, multi-platform. But what that means is you get to just write a single code base that you can then use across multiple platforms if you want. So I actually find that Flutter is very productive just to do Android development on its own. But if you want to do an Android app and an iOS app and perhaps support other platforms, Flutter gives you the means to do that all from a single code base. You don't have to write separate code for each particular platform. And as I mentioned, Flutter tries to fit into the platforms it lives on. So there's a material set of widgets which follow the material design system from Google. There's also a Cupertino widget set which follows the Apple HIG user interface elements that are present on iOS. Now, in terms of tooling, there's really great support. You can choose between Android Studio and VS Code, depending on your preferences, to do your development. In fact, you can use another editor IDE altogether and then just make use of the Flutter command line tools. But most people do tend to use either Android Studio or VS Code as their primary development tool. And in terms of the platforms, Android and iOS were the first ones, but web is now supported, at least in beta form. And Flutter has even more recently branched out to supporting desktop platforms, Mac OS, Linux, Windows, and they are themselves in beta alpha. And when I wrote these slides, Windows was in developer preview, but Windows is now very recently gone into alpha as well. So basically, even though that's quite not very mature yet, like already it's quite usable to build or at least prototype apps for Mac OS, Linux, and Windows using the Flutter SDK. So starting off with mobile apps, you can now have a single code base that also lets you branch off and deploy the same code to the web and to desktop. So it really covers pretty much all the platforms that you might care about as an app developer. Now, I've mentioned initially that Flutter is great in terms of its graphic support. Well, this just goes to show you, like, really Flutter is fantastic in terms of how it emphasizes excellent graphics performance. And you can really do some amazing things in terms of very bespoke custom graphics interfaces if you want to in Flutter. It's powered by the same engine library skier that Chrome and Firefox the Chrome and Firefox web browsers use under the hood, and it's also uses directly OpenGL and Meta on Android and iOS to get really high performant graphics without killing your battery life either. And that little video that was playing was like a bunch of examples from a competition that the Google Flutter team ran. I think it was last year, for people to design their own clock faces. Now, also Flutter has a really great ecosystem. So another reason why you might want to choose Flutter over something else is the fact that it has a really excellent community to participate in, and it has a fantastic ecosystem of packages. So similar, if for instance, anyone who might be familiar with JavaScript and Node and NPM, like Flutter has its own version of a package website called pub.dev, and there's already 7,000. Like, this is actually quite old. But there was 7,000 new packages published over the past year, and I don't have a total number count, but it's huge. There's an enormous variety of packages there all ready for you to use, basically libraries that you can make use of to kickstart your app development. The latest stats that Google published say that there are 90,000 plus apps in the Play Store. Like that's not like, it's not like app instances. That's different apps. So there's over 90,000 apps in the Play Store already that have been built with Flutter. So there's already, even in the short time that Flutter has been around, been a huge uptake for building apps on mobile platforms. Now, I don't know what the comparable number is on iOS, but given that Flutter does cover both platforms from a single code base, I wouldn't be surprised if there was a comparable number of apps in the App Store that have been built with Flutter as well. So there's been a lot of adoption already. And finally, of course, Flutter is open source, which means that there's all the codes are available there for you to make use of, and it's actually quite useful often to have a look at the way that the Flutter team themselves have built particular widgets to learn particular techniques or figure out how something's done in a particular way. But also, like, there's been a lot of buy-in from the community. So there've literally been hundreds of outside contributors who have contributed code to the Flutter SDK, and it's a very liberal BSD license. So there's not very many restrictions on what you can do with it. Finally, I wanted to mention the fact that there are some great online tools, Dartpad, and for those of you who do web development, you might have heard of CodePen. These are really good ways to try out Flutter really quickly. You don't have to install anything. Just hop onto either of them in a web browser, and you can be productive very quickly in terms of trying out different things. Dartpad has a whole bunch of examples, both simple and complicated, to get you started. There's also another site called Flutter Factory, which has a tutorial on how to build like a little simple browsing app for fruit and vegetables in this particular case. And I've grabbed it and actually just copy and pasted some of that code into Dartpad, into the standard Dartpad, just to show you what it looks like when you're like trying things out. And CodePen is great because people have used CodePen to publish a whole bunch of really impressive demos online. So if you search Google around, you'll find a lot of really fantastic demonstrations of what you can do with Flutter on CodePen. Now, the status of Flutter is that it's already quite mature. The reason I included this is that it's already at version, and even that's out of date because recently version 1.22 has been released. So they basically are now having a stable release every quarter. There are also beta and development channels that you can check out to see like what's coming down the pipe, as it were, like new features or if you need a particular bug fix. But really, there's a lot of work being done to make Flutter better all the time, but it's already a very mature system, and you can get production work done quite easily in it now. There's also Flutter-specific CI/CD service if you need it. There's a tool called Ride that's not only built to produce, that can produce animations for Flutter, but it's actually being rebuilt using Flutter. The new version of this tool is actually being built using Flutter's support for desktop and web. And a big new feature that's coming to Dart that people who perhaps have done Kotlin or Swift might want to know about is this thing called null safety. So that's very like literally within a month or two is going to be released, and that really makes Flutter much more comparable, or Dart language that drives Flutter much more comparable to Kotlin and Swift for those who've done some native development on Android or iOS. So finally, I'll just quickly show you how you do Flutter and what Flutter code looks like. And I mentioned this at the start, like Flutter has this thing called declarative UI. And that's a fancy term for what essentially is a simple concept. It just means that the user interface that you see on the screen comes from the application state being mapped onto the user interface. And that's quite a different approach from how people have built iOS or Android apps or desktop apps in the past, in that previously what they would do is the app would maintain state, and then you'd write all this code to essentially manipulate the user interface. So you'd go like, you know, if my state is this, do that. If my state changes to that, do this. Whereas this declarative UI approach, which was popularized by React on the web, essentially moves away from that and creates a new paradigm where basically what you do in your code is instead what you say is, I have this user interface and I have this state, and the framework or the SDK figures out how to do that for you. It figures, once you tell it this state marries up to this user interface, the library or the SDK does the rest for you and keeps it updated or updates it as necessary as your application state changes. You don't have to manually keep twiddling with all the little bits of user interface on the screen based on things that are happening that you're monitoring. All you have to do is simply specify the state, specify that this is the user interface, and how they essentially map from state to the interface. Now that's very, I guess, high level or very abstract way of describing what it does. So I also wanted to include, even though I don't have much time, a very basic example of Flutter code. And this literally is pretty much the hello world for Flutter. As you can see, it's actually, there's not a lot of boilerplate in Flutter. Like in about 8 lines of code, and that's very spaced out to be nicely formatted, you've got a basic app that will, if you put this into, say, Dartpad after this talk is finished, you'll see a basic hello world app running, displaying that text on the screen. So basically, what I wanted to show, having this little example, is like roughly what a Flutter app looks like in terms of the nesting. So as I mentioned previously, there's a center widget, which sits inside the runApp method, which centers whatever's inside it. And it has one child, which is just a text widget. And we're giving that text widget some state. In this case, it's hard-coded state, which is just a string hello world. But you could, for instance, imagine that this might be some piece of data that's manipulated in some other place in your app. And so what you would do is you would provide a means for the text widget to be given the new text. Say if someone's entered a new piece of text, or if you're showing a piece of text that you're perhaps fetching based on reading some API on the web somewhere, you would pass that in using a state management solution. There are many available. Some, like Redux, come from the world of React, but the most popular, or the place where Google recommends you start, is a package called Provider, which gives you a way to both manage pieces of state, like say text or other pieces of data that you want to keep track of, but also provides a very easy way of passing it into any widget anywhere in your app. Because as I mentioned at the start, your Flutter apps can be very deeply nested versions of this. And rather than having to pass these bits of data through every widget down to the very bottom child that needs it, something like Provider gives you a method of letting just those widgets at the very bottom of your tree, or in the middle of your tree, wherever they happen to be, access whatever piece of data they need. I don't really have enough time to get into the details of that, but really it's, once you get into it, you'll find that it does make sense pretty quickly how to manage your state in a Flutter app, and then essentially all your UI does is register for changes to the state and displays it per whatever kind of code you've written to show it. That, in a nutshell, is pretty much all I wanted to cover today. I know it's been a really whirlwind tour of Flutter. I've got a whole bunch of resources here, and there's plenty more. There's just an amazing amount of resources available on the web to help you learn Flutter or to get your questions answered once you start using Flutter. I've just called out some of the kind of starting points that you can use. The websites from Google themselves, flutter.dev, dart.dev, are excellent. They're just huge in their own right in terms of all the documentation they have for Flutter. I mentioned Dartpad, which is a great starting point. So you don't have to install the Flutter SDK or Android Studio or VS Code or anything like that. You just basically get started with just opening your web browser at that URL. Chrome is recommended. I think it works in Firefox and other web browsers too, but Chrome would be the best experience for that. Likewise, there's also an interactive tutorial. There's a couple of free courses that people from Google or Google have sponsored people to make on Udacity and App Brewery. There's a huge amount of content on the Flutter YouTube channel. Too much to go into now, but like really highly recommend you checking that out, because members of the Flutter developer relations team from Google have just done a great job making all those videos. I couldn't pass the opportunity to plug our Melbourne Flutter meetup, but of course you guys are in Auckland. But what is nice is that we, along with the GDGs in Australia and New Zealand, have essentially a combined Slack now that everyone is welcome to join. Please get in touch with me if you don't know how to join, but really if you Google for GDG ANZ or Australia GDG Slack, you should be able to get to it. I think it's also linked, of course, from the Melbourne GDG website as well. I'm actually a co-organizer of the Melbourne GDG as well. So yeah, if you can't find how to get onto it, get in touch with me or one of the organizers of your club here, and I'm sure you'll be able to get on board. We've got a pretty active Flutter channel, but we've also got lots of other active channels in the Slack. So yes, I highly recommend you, if you can, join us there and have a chat, especially in these times where we can't travel very much and actually see each other in person. There's also lots more resources. There's other chat channels specifically for Flutter on different things like Gitter, Discord. There's too much to cover. And of course, Stack Overflow is just brimming full of answers to all sorts of problems that people have come across in the past and had answered. And with that, I don't know if I've still got time for questions, but thank you very much for coming and listening. And yeah, if there are any questions, I'll be happy to answer them.
Awesome. We've got like about just a few questions we can quickly get answered, so I'll just bring those on now.
Sure. I'll still hearing.
Just there. Oh, that's the wrong one.
I'll just.
Sorry about that.
Move here, so I'm looking at you while I'm looking at the questions.
Yeah. So, just the first question: is it necessary to be familiar with Dart before learning Flutter, and which other programming languages should you be familiar with beforehand?
Oh, that's a great question. Yes, you do need to know a tiny bit of Dart, but really, if you're familiar with any C-like programming language, you'll be productive in Dart literally in a matter of almost minutes, if not just like an hour or two. Because one of the kind of key goals for Dart was for it to be easy to learn by anyone who's used a C-like language. So if you've done anything with C, C++, JavaScript, even Java, even possibly Kotlin and Swift and Objective-C, any of those kind of family of languages which are C-like, you'll be up and running in no time at all. So like, in fact, a lot of people basically learn Flutter and Dart at the same time. You can essentially learn one along with the other while you go through examples. And yeah, look, I've not heard of anyone who hasn't picked up very quickly, because that's the whole intention of Dart, is for it to be very familiar with anyone who's dealt with any other language.
Awesome. The next question was, could you recommend some resources to start learning Flutter? And we'll probably just post those links and everything and pass information on that you just showed us before.
Yes. Yeah, and
So,
like all those, I'll pass on a link to my slides, and on that last slide, I actually have those all those resources as URLs, so you can just click on them once you get to the slides and follow through to the various places. But yeah, a great place to start is the App Brewery or the Udacity courses. They're free. And like I think the Udacity one is not too long, so it shouldn't take you very long to get through that course and really get up and running very quickly.
yeah, awesome. Just another interesting question we have here is you mentioned the material and Cupertino widget sets. How hard would it be to make custom widget sets?
Oh, this is another brilliant question. I'm really happy someone asked this one, because yeah, that's one of the things about Flutter is the fact that really the material and Cupertino widgets are just essentially the two things that the Google team have built on top of the basic widget framework. But that's just essentially their take on building widget sets to a particular spec. What they've built on, though, is available for you to use as well. And it's actually really, really easy and very common for people to build their own custom widget sets, or to start perhaps with the material Cupertino widget sets and customize them to whatever design system or anything like that they like. So yeah, this is I think one of the big features of Flutter that perhaps I didn't touch on as much, is that it is very easy, especially compared to the trouble you might have doing this kind of customization, say in native Android development. Flutter is essentially almost made for you to customize to your heart's content, either the existing widget sets or start with kind of like the more primitive widgets that Material, for instance, builds on, and you can use those more primitive widgets to essentially build whatever you can imagine. It's actually very easy to do that.
Awesome. Well, sorry we cannot ask any more. We have run over time a little bit, but thank you
all right.
so much.
I did a bit long.
No, that is quite all right. It was a wonderful talk. So thank you very much to Maksim and Aurélien for the amazing talks. They were very lovely and very interesting, and we'll be sure to try to pass on all the resources and maybe even some more questions and post them on the Facebook in the next few days. Thank you very much for everyone who turned in today. We also have the sort of When the Google Home Mini as well, if you fill out the feedback form. So I believe moderators will be posting that in the YouTube link. So we really highly recommend any feedback, and thank you so much for along to our first event, and we hope you got something from it, and we wish the best for you now. So thank you, everyone. Bye.
Thank you. Bye.
Thank you. Bye.